So hello everyone, thank you for attending my talk. My name is Schatz and I'm a PhD candidate from North Carolina State University. I will be presenting our work on behalf of myself and my collaborators, Jing and Rada Chirkova. We developed an approach called trend surfing for efficient and effective retrieval of unusual temporal trends. So first, I'll give an overview of our work and what we accomplished. We formalize the problem of retrieval of unusual trends in the search space of temporal trends, which I'll describe. We show that exhaustive solutions to this problem are worst case intractable, and so we propose a tractable trend surfing solution that works for both numeric and categorical dependent variables. And then we also show experimental results indicating that the trend surfer approach is effective and efficient, and that it can reduce user efforts and their experience during their search for unusual trends. So just to give an outline of this presentation, I will start off with some motivation for our work and the problem that we address, and I will formally describe that problem, and then I will discuss some solutions, and finally I will show the results of our experiments and then summarize the takeaways. First, the motivation for our work comes from temporal data analysis. Temporal data include information about the valid time in the real world, and such data has emerged in many application domains, such as weather, biology, and more. Temporal data analytics often involves locating unusual trends in the data, along with the contributing factors that may impact these trends. For example, identifying unusual changes of interest can inform decisions that real-life users need to make with respect to the data. Unfortunately, the lack of presently available analytics tools causes data analysts to try to identify such temporal changes manually, either by applying their background knowledge about the domain or by exploring the data in a brute force manner. The goal of our work is to effectively and efficiently identify one or more unusual temporal trends from a fact table that are associated with a specific number of contributing factors to help analysts achieve this problem more quickly. So, for example, consider this fact table here, which shows some flight delay information. The fact table consists of a set of group by attributes, which collaboratively characterize the flights recorded in the table. There's a measure attribute, which describes the delay of the flight, and a temporal attribute, which represents the valid date of the flight delay information. This table encodes many trends of temporal changes. For example, the first two tuples here can be translated into a single trend, which describes the flight delay changes of the flights characterized by the values of the group by attributes. In this case, these are the flights departing from LAX, arriving at SEA, and being carried by DL. Also, the second two tuples here can be translated into another trend of flight delay changes, which is also described by the values of the group by attributes, characterizing flights departing from LAX, arriving at JFK, and being carried by DL. Additionally, we could group this table with respect to different group by attributes and generate even more trends. For example, here I've grouped the table by the origin attribute alone, using the average function for the aggregation. And so these four tuples give you the average of the measure value on January 1st and on January 2nd, and then the average values here form this trend. The trend is labeled by the value of the single group by attribute. In this case, the label is the origin airport LAX. Also, we could group the table by the destination attribute. The first two tuples grouped together are from the destination SEA, and so they would give you the average delay values on January 1st and 2nd for the destination airport SEA. And then the third and fourth tuples give you the average delay on January 1st and 2nd for the destination airport JFK. So in this way, we can form many trends of temporal changes from the fact table. Now, if data analysts want to find the most unusual trends associated with the group by attribute or contributing factor, then they would first have to generate all the trends that are associated with one group by attribute. Without any assistance, they would complete this task by manually enumerating all group by attributes and then aggregating the underlying table repeatedly with respect to these attributes. After that, in order to identify the most unusual trends, they would have to manually examine all of them together to get the answer. However, suppose that there was an off-the-shelf system that could help analysts out in this scenario. Specifically, after the analysts select the expected number of associated group by attributes or the impacting factors of interest, the system would automatically suggest the most unusual trends with the target number of attributes associated. In this way, the originally required manual efforts in generating and comparing trends are no longer necessary. So the goal of our work is to create such a system so that we can alleviate the efforts of data analysts in scenarios such as these. So now I'll formulate the problem that our work addresses. First, we must define the search space of temporal trends, and for this, we will let R be a fact table that has n non-temporal attributes, a temporal attribute T, and a dependent or measure attribute of interest. I'll be using the table from before as an example to describe the space. We also need an aggregation function, ag, and in our case, in these examples and in the experiments, we use the average function. Now let H be some subset of the non-temporal dimensions. In the search space, we construct a node for H by executing this SQL query shown here. That this query would group the data by the dimensions in H and by T and aggregate it according to the selected aggregation function. The node, the H node, would represent the temporal trends associated with the selected non-temporal dimensions. So for example, if we let H be the origin attribute in our table, then we can construct the H node by the SQL query shown here using average aggregation. And that would give us this table E, which has only a single non-temporal attribute origin. And the tuples here show the average delay values for the LAX origin airport on each of the corresponding dates. So temporal trends in an H node can be formed by selecting a specific value for each of the non-temporal dimensions. In our example, there's only one value for the non-temporal trend origin, so we would construct this trend by this SQL query shown here, which would select all the rows from E that have the specific value LAX for the origin airport, in this case, all the rows, and it would generate this trend of temporal changes. So now if we consider the entire table and we want to build the entire search space of temporal trends for this table, then we would have one H node for each set H that's a subset of the non-temporal dimensions in the table. And the H nodes are organized in this way by their depth, where the depth of an H node is the cardinality of H, or the number of non-temporal dimensions associated with that node. So there's also navigation links that go between any two nodes in adjacent depths when one node in the earlier depth is a subset of the node in the latter depth. In our case here, for this search space, we have 3 nodes at depth 1, one node corresponding to each of the 3 non-temporal dimensions. We also have 3 nodes at depth 2, one corresponding to every 2 subset of the non-temporal dimensions, and then there's just one node at depth 3 in this case, corresponding to the full set of 3 non-temporal dimensions. There are navigation links between nodes from depth 1 to their supersets at depth 2, and nodes at depth 2 to their superset at depth 3. In general, the full search space contains 2 to the n nodes, where n is the number of non-temporal dimensions, and appropriate navigation links are included as well. Outlier detectors can be used to rank the temporal trends from the search space from most unusual to least unusual. Some popular existing outlier detectors include principal component analysis, or PCA, k-nearest neighbors, or KNN, and the clustering-based detector, or CBLOF. Finally, we define the problem related to this search space as follows. Given a temporal fact table with non-temporal dimensions, a temporal dimension, and a dependent attribute, an aggregation function, an outlier scoring function of interest to the data analyst, and a number of target group by attributes, and an unusualness criterion. Our goal is to effectively and efficiently identify one or more unusual temporal trends at depth k in the search space of temporal trends. That is, we seek to find trends that satisfy the unusualness criterion with respect to the outlier scoring function. For the unusualness criteria required by this problem statement, we find that the following two criteria are useful. Criterion A states that a temporal trend is unusual if it is one of the top 5% outlier scoring trends with respect to the outlier detector, and we selected that cutoff of 5% from the standard cutoff used in statistics. And criterion B states that a temporal trend is unusual if it's an element of the top scoring outlier cluster, where the cluster is determined by some off-the-shelf clustering method. Next, I will introduce some solutions to this problem statement. First, I'll review an exhaustive brute force solution that is unfortunately worst case intractable. The exhaustive procedure first extracts and ranks all temporal trends at the desired depth k in the search space, according to their scores by the provided outlier scoring function f. Then, the procedure simply just returns the desired number of top-ranked trends after the ranking. As for the runtime of this approach, we prove the following theorem in our paper that states that for a range of depths k around the depth n/2 in the search space of trends for the fact table R, the time complexity of the brute force procedure is in big omega of a to the n, where a is greater than 1. So in other words, the brute force procedure is in some cases exponential in the number of non-temporal dimensions associated with R, so it's worst case intractable and is therefore not a suitable solution to the problem in all cases. With this in mind, due to the limitation of the exhaustive solution, we propose a heuristic solution that is tractable. The proposed solution is a greedy search strategy that relies on the following intuition: that the group by attributes associated with unusual trends in the former levels of the search space will also be associated with unusual trends in the latter levels. Our approach, which we call trend surfing, takes as input the temporal fact table R, the outlier scoring function selected f, and the target grouping depth k, or the target number of associated attributes. I will show the algorithm with respect to the example fact table discussed previously. This fact table generated the following search space that we saw before. So for our trend surfing framework, with the greedy strategy, we would first find the group by attributes associated with the most unusual trend at depth 1. And then we would go from there to find the group by attributes associated with the most unusual trend at depth 2. But for this search, it would limit the scope to only the remaining group by attributes that can be used in conjunction with the group by attribute found at depth 1, instead of having to consider all possible combinations of two group by attributes. So then this would allow us to select the top node as the node at depth 2 associated with the most unusual trend. This procedure would just continue iteratively until the target grouping depth k has been reached, at which point the top scoring trend from the each node identified would be returned and the search would terminate. So all that remains is to introduce our proposed strategies for choosing the next node in the search space. We have two strategies. First, Trend Surfer 1 strategy is to select from the available nodes the node whose top outlier scoring trend scores highest among all top trends from each available node. That is, the node whose top trend has the maximal F score, or outlier score. The intuition behind this strategy is that global outlier trends tend to be local outliers within their respective nodes. In this example image shown here, the plus signs are local trends within a single node of the search space, and the squares are non-local trends in other nodes of the search space. We can see here that the point P1 is an outlier within its set of local trends. So the Trend Surfer 1 strategy here would propose P1 as the expected global outlier. Unfortunately, as you can see, this intuition does not always hold. In the example shown here, even though P1 is an outlier with respect to the other local trends inside of its node, it's not an outlier globally with respect to all trends. So with this in mind, we propose an alternative strategy of trend surfer 2, which is to select from the available nodes the node whose top outlier scoring trend is furthest from the center of mass of all trends. The intuition behind this strategy is that outlier trends lie far from the center of mass, or the average trend. In the example here, we've drawn a horizontal line representing the center of mass, or the average of these trends. And we can see that P1 lies close to the center of mass, so it would not be selected by the trend surfer 2 strategy. Instead, P2, which is the true outlier here, would be selected since it's furthest from the center of mass. As for the runtime of the trend surfing approach, it is quadratic in the number of non-temporal dimensions for the fact table R, as we prove in Theorem 2 in our paper. Therefore, our approach does provide a runtime improvement over the exhaustive solution presented earlier. Now that I've introduced the solution, I will show the results from some of the experiments we conducted to test it. In our experiments, we considered 3 different real-world data sets, one about flight delays, whose dependent attribute is the arrival delay, and whose temporal dimension is the date of each flight. This is the data set that we've been looking at so far. And then we have 2 other data sets, house pricing and car retailing, where the dependent attribute of interest is price in both cases, and the temporal dimension is sale date in both cases. All 3 of the data sets have 4 non-temporal dimensions. And we wanted to show that our approach works for both numeric and categorical dependent attributes. So we use the dependent attribute arrival delay from the flight delay dataset in both forms, numeric and categorical. We use the 3 popular outlier detectors mentioned earlier, PCA, KNN, and CBLOF, as the outlier rankers for our experiments. First, we explore the effectiveness of our approach. To this end, we ran our approaches on each of the 3 data sets using the average aggregation function, and we used each data set in combination with each of the outlier detectors and each of the possible target depths, 1, 2, or 3. To measure the effectiveness of our approach, we used both of the unusualness criteria discussed previously. Specifically, according to unusualness criterion A, which states that a temporal trend is unusual if it's one of the top 5% outlier scoring trends, we measured the effectiveness by ranking the output trend according to its outlier score against all the other trends. And then we report the absolute rank of the output trend along with the percentage score. According to unusualness criterion B, which states that a temporal trend is unusual if it's an element of the top scoring outlier cluster, we used k-means to cluster the trends 14 times, using 2 through 15 as the number of clusters. And we report the percentage of these 14 cases where the output trend was placed in the top scoring outlier cluster. To preview the results, we find that in most cases in these experiments, the trend surfer approach is able to effectively identify top-ranked outlier trends, which satisfies criterion A, and trends in the top-ranked outlier cluster, which satisfies criterion B. We also find that trend surfer 2 outperforms trend surfer 1 in many cases, as we expect. So now let's take a look at the results. First, we have effectiveness results with respect to unusualness criterion A on the numeric dependent attributes of all 3 of our datasets. The white bars here represent the performance of trend surfer 1, and the black bars represent the performance of trend surfer 2. The x-axis indicates the dataset, the outlier detector, and the target depth, which together comprise the specific test case. And the y-axes indicate the rank of the output trend and the percentage score of the output trend. In many cases, both trend surfer approaches are able to return the top-ranked outlier scoring trend. However, we can see there are some cases where the output trend has a worse ranking, specifically for trend surfer 1. Though in most of those cases, we see that our approaches identify trends in the top 1.5% of all trends, according to all 3 of the outlier scoring functions considered. Also, we see that in many cases, trend surfer 2 does outperform trend surfer 1, even though both strategies perform well overall. Next, we have effectiveness results with respect to unusualness criterion B on the numeric dependent attribute from the flight delay dataset. So the first column here indicates the test case, which is comprised of the outlier detector and the target depth. And then here we see that our approaches perform well overall. There are some cases where the trend surfer approaches are not able to return a trend that's in the top scoring outlier cluster, but overall, in most cases, the approaches are successful across all the outlier detectors, all target depths, and all cluster counts, with an average total effectiveness of 77 and about 89% respectively. Again, we see that trend surfer 2 outperforms trend surfer 1 here. Finally, for effectiveness, we have the effectiveness results with respect to both unusualness criterion on the categorical dependent attribute of the flight delay dataset. So for this, we bind the dependent attribute of the dataset to make 10 categories. Again, here the first 2 columns indicate the test case. Our approach is able to identify unusual trends in all cases, returning the top outlier scoring trend in 12 of the 18 cases shown here, and in all other cases, a trend within the top 0.2% is returned. Although the returned trends were in the top scoring outlier cluster in every case for this experiment. And the performance of trend surfer 1 and 2 are equivalent in this case. So to summarize so far, we have now seen that in most cases in these experiments, the trend surfer approaches are able to effectively identify unusual trends satisfying both unusualness criterion, and trend surfer 2 outperforms trend surfer 1. Next, we explored the efficiency of our approach to make sure that it would be faster than the brute force approach. So to this end, we again ran our approaches for the same test cases as before, but this time we varied the number of tuples, or the size of each dataset, and the number of non-temporal dimensions in each dataset, so that we could analyze the impact of size on the approach efficiency. In addition, we ran the exhaustive solution as a baseline approach, and we measured the efficiency of each approach according to the runtime in seconds. To preview the results for efficiency, we overall found that the exhaustive approach is always slower than the proposed trend surfing approaches, and the runtimes for trend surfer 1 and 2 are roughly on par with each other. So let's take a look at those results. Here we show the runtime for the exhaustive baseline solution, as well as for both trend surfer approaches. Please note here that the trend surfer 1 and 2 approaches perform so similarly that their lines overlap in the graphs. The y-axis here shows the runtime in seconds. Section A shows the results when varying the number of tuples in the size of the dataset. Here, our trend surfer approaches are only slightly faster than the baseline when we use PCA or CBLOF as the outlier detector. But for KNN, our approaches are substantially faster. After all, KNN is the slowest of these outlier detectors, so there's much more room for improvement in speeding up the search. B here shows the results when varying the number of non-temporal dimensions in the dataset. And although the baseline is nearly as fast as our approaches when there are only 3 or 4 non-temporal dimensions, our approach shows improvement when there are 5 non-temporal dimensions. And we do expect that if we were able to increase the number of non-temporal dimensions here, then this would provide further evidence of this trend. Also, we point out that the runtime of trend surfer 2 is on par with that of trend surfer 1. So even though trend surfer 2 was able to outperform trend surfer 1 in terms of the effectiveness results shown earlier, it takes no more time. So overall, now we've seen that the exhaustive approach is always slower than the trend surfer approaches, and that the runtimes for trend surfer 1 and 2 are roughly the same. Finally, the last test we did for our approach is a user study so that we could see how our approach could actually help users in their navigation of the search space of temporal trends. First, our first user study explored the hypothesis that there's a correlation between a trend's interestingness and its unusualness. This just implies that the unusual trends returned by our approach are actually the ones that data analysts are interested in. So for this study, we created a set of 10 temporal trends containing 2 top scoring outlier trends as unusual trends. For example, this one here. and 8 random trends as typical trends, such as this one here. We then asked the users to rate each of the 10 trends based on the degree to which they were interested in them. We measured the success of the hypothesis using precision and recall, where precision is the proportion of trends of interest that were unusual, and recall is the proportion of unusual trends that were of interest. We also used the F1 score, which is the harmonic mean of precision and recall, and balances the two. For the results here, we asked 4 users to work with the flight delay dataset and 4 to work with the house pricing dataset. The precision, recall, and precision and recall are shown for each user, and then the precision, recall, and F1 score averaged are shown for each dataset. The results here demonstrate the validity of our hypothesis. Although for some cases, the precision and recall scores for individual users were low, the average precision and recall are quite high, and so are the F1 scores. So this suggests that users do find unusual temporal trends to be of interest. So we've deduced that data analysts are in fact interested in unusual temporal trends, and therefore the trends that would be output by our approach would be useful to data analysts. For our last user study, we explored the hypothesis that the trend surfing approach can reduce the length of user paths if they were to search the space manually. This would imply that our approach can be of assistance to data analysts. For this study, we asked users to find the top scoring outlier trend in 2 different settings. The first was we asked them to perform an unassisted navigation through the search space of temporal trends. And in the second scenario, we asked them to do an assisted navigation where we gave them the node at depth 1 from which to start their search. We measured the success of the hypothesis by comparing the length of the search paths between the 2 settings, and we also recorded user ratings of the importance of the trend surfer recommendations to them. So for the results here, we again asked 4 users to look at the flight delay dataset and 4 to look at the house pricing dataset. The first 2 columns indicate the data domain and the outlier detector assigned to each user. And the results demonstrate the validity of our hypothesis. In many cases, TrendSurfer 2 was able to reduce the length of the user search paths, but in cases where there was no path length reduction, these are all cases where the user was able to independently identify the target trend using the minimal path length on their own anyways. Additionally, TrendSurfer did receive positive ratings from users in most cases, even in those cases when the users were able to be efficient on their own. So to summarize this user study, we find that the TrendSurfer approach could alleviate user efforts and improve their search experience. So finally, I'll summarize all the key takeaways from our work. We first formalized the search space of temporal trends along with the problem of retrieval of unusual trends from the search space. We showed that that the exhaustive solutions are worst case intractable and therefore may not be useful in many cases. So to address this, we've proposed a tractable trend surfing solution that works for both numeric and categorical dependent variables. And finally, we performed experiments indicating that TrendSurfer is an effective and efficient approach for identifying unusual temporal trends, and that TrendSurfer can alleviate user efforts in their search as well as improve their experience. So thank you so much for attending my talk, and I'm happy to answer any questions if there are some.